So one of the biggest applications of heat that we have in the real world is that of thermal expansion. Basically what this means is that molecules get further apart or closer together as the temperature changes. We can talk about this in terms of linear expansion, dealing with something that's two-dimensional, such as the length or the width of a piece of steel. That will increase in length when it's heated, and it'll contract when it's cooled. This is noticeable in longer, thinner objects. We can't see the width of it increase as much just because it's not as extreme as the length. So the standard way of demonstrating this is we will have L0 here, the original length of the object, and then delta L will be the change in length, so how much it expands or contracts. We need to consider three different things when we determine how much the length will change. How much the temperature changes. So if the temperature increases by 160 degrees, the length of the object will change twice as much than if the temperature changed by 80 degrees. The change in length is proportional to the original length of the object, so a longer object will expand more than a shorter object. And some substances, may expand more than others based on some of their chemical properties. So the formula, delta L equals AL delta T. Delta L is the change in length. A is the coefficient of expansion, which we'll look at in a minute. L is the original length of the object, and delta T is the change in temperature. So with solid objects, we generally talk about linear expansion. With liquids and gases, though, we generally talk about volume expansion. Volume being 3D, it's easier to see in a liquid or a gas. Very much the similar formula. We use delta V for the change in volume. That's a Greek letter beta. It kind of looks like a B, just a different variable because we're dealing with volume expansion. V for the original volume, and delta T for the change in temperature. So in the data booklet, you have this table of coefficients of expansion. So we have linear expansion for some solid objects on the left, and then near the bottom on the right side we have volume expansion. The key thing to all of these, and I can't be clear enough about this, is all of these coefficients are in scientific notation times 10 to the minus 6. So every single one of these is times 10 to the minus 6, and so on in both columns. That's because the change in length is so very small compared to the original length, and it's just easier to put times 10 to the minus 6 at the head of the table rather than to write it out every single time.